Today I'm going to share some of my experience working on the Suspend Resume in operating systems. And these projects, I'm working with other collaborators such as Li Wei, which is sitting on the front row, and also Xiang Yu, which is another undergraduate at Purdue, and also Felix. So nowadays, many mobile devices and IoT devices have some short-lived tasks. So for these kind of devices, they usually sleep for a long time and wake up frequently. For example, for smartwatch, it will suspend and resume 72 times per day on average. And also, each task is really short. And according to Apple Watch design guideline, each user interaction should be less than 10 seconds. And also, for the background tasks, the time is even shorter, which is less than 1 second. So now we know that IoT and mobile devices, they suspend and resume really frequently. So let's move on to the OS suspend and resume workflow. So for the suspend, it will start from sync file system, and then it will freeze all the tasks. And then the OS will call each individual I/O drivers to put I/O devices to a low power mode. And finally, the main CPU will shut down. And for the resume, it's a mirror process of the suspend. However, the problem is the suspend resume is expensive. And this is a known problem for a long time on the desktop and servers. And on the desktop and servers, the suspend and resume is slowed down by SATA and USB devices. But these devices are rarely suspended, so this is not a problem for the servers and desktops. But things are different on the IoT and mobile devices because, as I mentioned earlier, they have many short-lived tasks. And for example, on Samsung Note 4 smartphone, each suspend and resume will take 500 milliseconds. And if we consider the mobile sensing benchmark, 43% of the total energy is consumed by the suspend and resume, which is quite a lot. So therefore, we need to understand the suspend and resume on IoT and mobile devices. We profile the suspend and resume on 4 different platforms, including Nexus 5 and Samsung Note 4, which are 2 popular smartphones. And we also profiled on the Samsung Gear, which is a smartwatch. And we also did the same thing on the Panda board. They use different SoCs from different vendors. So here is the absolute latency of the suspend and resume across 4 different platforms. And as you can see that the latency varies from tens of milliseconds to hundreds of milliseconds, which is pretty slow. So if we have a breakdown of the entire suspend and resume, we can see that the red bar, which represents I/O power transitions, dominates the entire suspend and resume. So that's why the suspend and resume is slow, because the I/O power transition is pretty slow. And if we take a step further, at least the top 2 devices on 3 platforms, which use most of the time. So as you may see that different platforms have different top I/O devices, which means that slow I/Os are diverse. And here is the number of different I/Os on each device. So for each device, there are over 100 I/O drivers that contribute to the total I/O power transaction delay. So also the slow I/Os are various. So since the power transition is really slow, why don't we make it asynchronously? So there actually one approach that overlaps the power transitions of different I/Os. But it has own problem because, first of all, the hardware has its implicit dependencies. And also, the OS driver does not have the knowledge of what other I/Os depends on. So for example, if you turn off one device, then the other device may be dependent on the first device, so which is bad. Therefore, Linux kernel community has a long debate over this asynchronous power management approach. And right now, they are still very conservative about this. So therefore, we want to address this problem in a different approach, which is offloading the OS suspend and resume to a very weak core. So it has dedicated hardware which is a weak core, to execute the OS suspend and resume. And also, we need to build a virtual executor that's running on the weak core that is able to run the suspend and resume on IoT devices. Some modern SoC incorporate those kind of low power cores. For example, on Apple SoC, they have motion coprocessors which can collect data from step counter and GPS sensors. Usually, they share the same I/O and memory bus, which allows them to access the individual I/O devices. And also, they have the incoherent cache domain and the heterogeneous but similar instruction set, which provides the hardware manufacturer the flexibility to design the low-power cores which can run more efficiently. And also, according to the previous study, weaker cores are ideal place for OS to execute suspend and resume. And this is because of two reasons. First of all, the weak core has a much lower idle power consumption. And secondly, kernel execution favors the weak cores because of the kernel execution's characteristics, such as smaller working input set and also less predictable control flow. So right now, I introduced the hardware requirement. Let's move on to the software challenges. So remember, our goal is to execute the suspend and resume on a weak core, which is incoherent cache domain and ununified instruction set. So one thing might come into your mind is probably we can carve out the suspend and resume from the Linux kernel, but it turns out it's not feasible. Because first of all, the modern kernels are beasts. They are very complicated. And secondly, the suspend and resume are also complicated. And more importantly, commodity kernel are rapidly evolving. So whenever there's a new kernel released, the computer scientist has to go back and carve out the suspend and resume code again, which is quite painful. Therefore, I will present our own approach, which is running a virtual executor that on the top of the weak core that is able to execute the unmodified kernel suspend and resume path. And as a side note, so probably you guys are familiar with the virtual machine. So for the normal virtual machine, it usually runs on much powerful PCs. But from our perspective, we are exactly doing the opposite way. We are running the virtual machine on a much weak core. And this is pretty amazing. So this is the system overview. On the left-hand side, we have the commodity system, where the main CPU is responsible for the entire suspend and resume. And on the right-hand side, we have our system. So at the beginning of the suspend, the main CPU will shut down and offload the suspend and resume work to the weak core. And the weak core will take the binary from the main core's kernel and translate and execute the suspend and resume functions. And at the very end of the resume, the weak core will bring the main CPU back. So some of you might have this thought in mind: does this really work? Because usually when you do binary translation, it will incur a lot of overhead. And this is a problem in our early experiment. For example, we run the same function natively on the big core and compare the performance, and we see that there's over 20x overhead slowdown. So the main reason behind that is the commodity binary translators are generic and conservative. And for example, the CPU status register are often emulated, and also it has to frequently go back and check the interrupt flags. So therefore, we need to some aggressive optimization on the binary translator. We optimize our design in 4 different directions. So first of all, we exploit the instruction set similarity. So we know that we are going to run our front-end code, which is ARMv7, on our ARMv7M architecture. So they have the same amount of registers and the similar instruction format. Therefore, we directly use the hardware registers. And this is also common on Intel's architecture. And secondly, since commodity on commodity binary translators, the stack pointer is often emulated, but we directly use the hardware stack pointer. And for the third part, we reduce the frequency of checking the interrupt flags, because in the suspend and resume, the most common exception or interrupts are from power transition notification completion. So therefore, we don't need to handle them immediately. And for the last part, we know that Linux kernels are mapped linearly. So therefore, whenever there's a memory access, we directly check the bound and apply an offset. And whenever there's an I/O access, we go through a software page table and do the address translation. So in this way, we can get rid of the fully fledged software MMU. And this is our current implementation. So we test our design on the TI OMAP 4 SoCs. And we take a generic binary translator, which is QMU, and refactor from 2.6 million lines of code to 50K lines of code. Also, in order to add the support for our new backend, which is ARM v7m, and also in order to achieve the optimization that I mentioned previously, we add 4.5K lines of code. And more importantly, this is the first time that we can actually run a virtual executor on top of an embedded core, which is amazing. So in order to test our system design, we use 3 different macro benchmarks, and we use the number of CPU cycles as our performance metric. So as you can see, we take the benchmark and compile and natively execute on the big core, and this will give us the baseline. And if we take the same benchmarks and compile and execute on the small core, and this will give us the upper limit of our design, because the compiler knows the source code, so they can apply any optimizations. Besides that, we also do the binary translation on the same functions and under 2 different versions. One is unoptimized, one is optimized. And as you may see from the graph, that compared to the unoptimized version, we achieve a 5x overhead reduction. And if we compare with the native execution, we are actually sit within 2x of the native execution, which is pretty good. So if we go back and plug those numbers back to our suspend and resume scenario, we actually could save 70% of the energy during the suspend and resume. And if we plug those numbers back to the mobile sensing benchmark, we can extend the overall battery life by 30%. And to sum up my presentation, so first of all, we know that suspend and resume is pretty slow on mobile and IoT devices. So therefore, we profile the suspend and resume on different platforms. And we observe that the main reason for the slow suspend and resume is because of the slow I/O power transitions. Therefore, we want to offload the entire suspend and resume to a weak core, which has incoherent cache domain and a heterogeneous instruction set. So the key idea of our approach is to binary translate and execute a modified kernel on the weak core. And for the mobile community, we can vastly improve the energy performance during the suspend and resume. And more importantly, for the OS community, we are actually the first one to build and run the virtual machine on the weak core. And no one has done this before. Thank you. And I'm ready to take any questions.